Hello community! Today we start our parameter efficient fine-tuning with multiple LoRa's. So what is the idea behind our low rank adaptation? Now, it was inspired by the observation that our pre-trained or huge pre-trained LLMs have a low intrinsic dimension and can learn efficiently despite this dimensionality reduction. So the team of LoRa hypothesized that the updates to the weights during the adaptation can also have a low intrinsic rank, the low intrinsic rank of our weight tensors, of our weight matrices. Great. So we have LoRa, our low rank adaptation for our self-attention module weights. And here we have our weight tensors for the query, for the key, for the value, and for the output projection matrices, respectively. So you can apply LoRa only on a subset of the matrices based on empirical finding or for the sake of parameter efficiencies. Now, you know that the most important idea of LoRa is that given a weight matrix W, the update is represented as a matrix factorization, and in our case, a low rank decomposition. So we have here the W0, this is our original pre-trained weight matrix. And then we have here an update value. And we approximate this update value with a matrix factorization. And here we have LoRa. And LoRa is simply a simplified form of our singular value decomposition. And we go here with the matrix B and the matrix A. Now, you know that those are the trainable parameters. And this delta W is here our low rank update. Beautiful. Now, you remember that given that this is a low rank adaptation, that the rank R is much smaller than the original dimension of our weight tensor W. And during the fine-tuning or the efficient parameter fine-tuning, the W0 weights remain frozen and only our matrices A and B are updated throughout the training. This is the theory of LoRa. Now, the low rank decomposition is the most important factor to save time, to be fast, to save money, and achieve almost the same precision as a full-fledged fine-tuning. And you remember, the trick is here the dimensionality of our matrices. So, our matrices A and B are of different dimensions compared to W0, and their size is based on a chosen rank. You chose here for your system a specific rank, and the beauty is a low rank is also providing good results. So the rank R is chosen such that it is really small, that here the minimum of D and K, if our original weight matrix is of size D times K. Beautiful. Now, of course, since we have that the W weight is B times A, it follows here that the dimension given of W, that the change in W has the same dimension as W, therefore B times A has also the same dimension, and then it follows that if we have W with D times K, that the dimensionality of our matrix is for B, D times R, and for A, it is R times K. Beautiful. So the product B times A therefore has the dimension D times K, which matches the exact dimension of our original weight tensor. This is the main idea, that we have here low rank adaptation matrices that perform here the mathematical operation for us in a low dimensional subspace. So when you apply updates to the model, you are efficiently only modifying a lower dimensional subspace of the complete weight space, the weight tensor space, now represented by the matrix B and the matrix A. And of course, since we have here this beauty of here the singular value decomposition, the subspace now is chosen in a particular way in the matrix factorization that it captures now the most critical aspects of the update while ignoring less important variation. And this is exactly what you know from eigenvalue, eigenvector representation, square root of singular values, and you know all of this from mathematics. For Ben, a simple example so you can imagine here what's going on. Now, imagine we have from our pre-trained LLM a pre-trained weight matrix W0. And our parameter D and K it's a matrix of the size 1000 times 800. So if you do a full-fledged fine-tuning, you have exactly 800,000 parameter that you have to store in your compute and you have to fine-tune to train with your compute infrastructure. Now, if we choose to not go with the full fine-tuning, but with the low-rank approximation in a parameter-efficient fine-tuning, we now decide, hey, let's go with R equal 10. This is already high, Ben. So this would give us now, for example, as I showed you the dimensionality of the matrix B and of the matrix A, that B has 1000 times 10, and A has 10 times 800 in the dimension. So we have here 10K parameter matrix and an 8K parameter matrix. So in total, now if we do here this more efficient fine-tuning, we now have 18,000 parameters. And this is a significant reduction from the original 800,000 parameters. The beauty is we have a reduction in complexity in multiple dimensions. So as I just showed you, the parameter count goes down and significantly from 800,000 to 18,000. And remember, because of matrix factorization and singular value decomposition, we are limiting ourselves to the most important subspaces. But we have the strongest and the most potent subspaces still in our calculation. For the training, for the update, for the learning here, we only learn now 18,000 parameters. And of course, if you have only 18,000 parameters, your computational load is just, it's so funny, it's a joke. You say, yes, let's do this in 5 seconds. So this is the reason, this is the beauty here of our parameter-efficient fine-tuning with a low-rank adaptation as a matrix factorization applied on the weight tensors of our LLM. Great. In total, short summary, PEFT LoRA advantages, drastically reduce the number of parameters. And now comes the beauty. Since the original pre-trained weights of our pre-trained LLM are frozen, we can now go on and have multiple LoRa models for various downstream tasks built on top of this pre-trained LLM. This is now something I will focus here the rest of my video on. And of course, you know that LoRa is here orthogonal to many other parameter-efficient methods, so you can combine LoRa with a lot of other methodologies and further improve here either the reduction of complexity or the speed of computation. The performance now of our LoRa is absolutely comparable to the performance of a fully fine-tuned model. I will show you this code and execution in my next video. And the beauty is your adapter weights can be merged, but be careful because there's another better opportunity with the base model. So even if you add additional weight tensors to our model, you can merge them and then you have no delta in the interference latency at all compared to the original model. So now we are in the main topic, multi-LoRa adapter models. How beautiful are they? Now, you know there's a simple recipe to fine-tune a transformer-based large language model, visual language model, whatever, using here our fine-tuning methodology that is based on a low-rank adaptation. At first, you need a pre-trained model. Beautiful. Take a Mistral model, for example. Then, and now this is now if you think you know LoRa, haha. Now we create a configuration file where you define LoRa-specific parameters. Do you think you know all 16 specific parameters and their interdependencies? If not, we go on. Then, of course, with the classical command get PEFT model, you have here, you wrap your base model to get a trainable PEFT model. And if you have this model is like any other model. You train or you fine-tune here, in this particular case, the PEFT model as you would normally train here any other LLM. Beautiful. Very short example in code. Transformer, you have your auto model for sequence-to-sequence language modeling. From the PEFT library, from the Hugging Face PEFT library, we import get PEFT config, get PEFT model, LoRa config, and from Hugging Face, we take here from Big Science here one LLM that we choose here, our tokenizer for the same, and then, as I told you, PEFT config. So we have here LoRa, because there are multiple PEFT modalities. We go here for one PEFT opportunity, LoRa, and our LoRa config, we just say, hey, for the task, sequence to sequence, what a coincidence. We have then invariance mode, here we have here parameters, and I look at the parameters in a second. And then, you have your auto model here from Hugging Face, from a pre-trained model. This is your Big Science MT0 large model. And then you just say, hey, get the PEFT model. You have your original pre-trained LLM and the PEFT configuration. And this is it. Now you have a new model. However, the beauty or the power or the interesting is in the PEFT configuration. Here we have here the class definition of our PEFT library, the LoRa configuration. Maybe you have never seen this before, and it is beautiful. Look what we can do with this thing. And for Ben, hey, look here, I've listed you all 16 LoRa configuration parameters you can set to optimize a singular LoRa adapter model. So you notice, at first we have the LoRa attention dimension, then we have the alpha scaling parameter for LoRa, then we have the dropout probability for the specific LoRa layers, and we go on. But if we just focus here on the attention dimension and the alpha parameter, this is really something fascinating. So I will show you here the interdependence here of this parameter, especially if we go from one LoRa to a multi-LoRa, because then it really gets interesting how you build here some coherence of the different LoRa modules. Now, simplest example, create here a LoRa model from a pre-trained transformer model. Now we take a T5 model. So again, you notice you have so many opportunities. Transformer, PEFT, LoRa model, LoRa config. In the LoRa config here, you can say, hey, what is the task? What is my rank? What is my scaling factor? And now look, now we have something that is really interesting. The target modules. And you might say, yeah, of course. Those are the query tensors and here the value tensors. And this is it. Well, not at all. We are just scratching on the surface. Now it gets really interesting. Have a look at this. Yeah. So we continue to say, hey, from the pre-trained, we load here the T5 model from the Hugging Face. Beautiful. And then we say, hey, you see another way to do this LoRa model. You take the original T5 model and you have now your config, your LoRa configuration with your specified target modules. And you give it a name and you can call this LoRa model default or whatever you like. So the name of the adapter model is free to choose for you. But let's focus here on this, because those three parameters are the most interesting parameter, and doing this video, I learned a lot about them. So, what is the simplest method I could find to understand what matrix or what tensor structure you want to apply LoRa on? Remember, LoRa is a matrix factorization methodology, and we, for example, we can choose SVD, the singular value decomposition, or then this is then the LoRa. So to find out on which specific transformer layer and module in the transformer you want to apply LoRa. A simple trick for you. I just go import here my PEFT library and my transformer library from Hugging Face, and then I say, hey, I take any model from Big Code Star Coder base. So a code LLM, a very small one. And I say, hey, show me the model. And the beauty is, I need here the complete layer structure of this model to understand where to apply LoRa on. Let's have a look at this. Yes, we download, and then here we have here big code for a causal language modeling. We have a transformer model, beautiful. We have embedding, we have a dropout, then we have here the code block here, the layer norm, and here's our attention module. And now you see here, talking about here the target modules. This here, in this particular model, they call this linear layer here C underscore attention and C underscore projection. And they have an attention dropout and a residual dropout. And a layer norm, and then of course they have here the multi-layer perceptron, the feed forward, and they have here a C underscore fully connected, I suppose, and a C underscore projection. Then they have here an activation function, non-linear activation function, and a dropout function. And then they have a layer normalization and so on. So you have, for your particular model, this model, I go there, I look at the model, I look at all the layers to understand this is the original layer structure of my model, and then I decide on which layer to apply LoRa on. And it is not always the same. And you can do a lot of optimization if you have here, if you choose the best layers. For Ben, if you just see this for the first time, no problem. Or any viewer says, oh, this looks beautiful. What exactly is this? I tried to write here a short summary. So you see here for every layer, I write here a short summary. And if you look here at the big code block, we have here the layer normalization, and then here the C attention, linear layer from computing combined attention keys, query keys, and the values from the input token. And the projection is a linear layer for projecting the output of the attention mechanism back to the dimension of the original model, and the dropout layers. And if you notice, beautiful. If not, here is the short explanation for you. I personally said, strange. So I said, hey, I look back at the original publication, LoRa, October 2021, what they recommend. And here I have here the original literature, and they tell you here, we, the author or the inventor of LoRa, we only apply LoRa to the weight of the query and the weight tensor of the values in most of our experience for simplicity. So what you see that the target modules of LoRa are always Q and V, this is not the case. This is just the simplest case. And the potential of optimization in all the different layers is unbelievable beautiful. So I limited myself here to the classical way because I did not understand that LoRa opens up here to all weight tensors in all the different layers. Before we do here some recommendation and some numerical values, please keep in mind there is a correlation between the original weight tensor and the space, and here the delta W. Because if you look again at the original literature, they talk about an amplification factor for LoRa. You can read this in detail. Just to give you an idea, if you choose here a LoRa rank of 4, the amplification factor can be as large as 20, which is the recommendation of the original authors of LoRa. And they say, hey, in other words, there are generally speaking 4 feature directions in this subspace in each layer out of the entire feature space from the pre-trained model W that we need, or that needs to be amplified by a very large multiplicative factor of 20 in order to achieve our reported accuracy for the LoRa learned fine-tuning downstream specific task. And one should expect a very different set of feature directions, remember SVD, to be amplified for each different downstream task. This is alpha, the amplification factor for LoRa, for the LoRa layers in our multi-layer structure of the transformer that we apply on. So I haven't been aware before how sensitive this system is here for the rank and the coupled factor of alpha. You can achieve some impressive performance increase if you fine-tune this for your downstream specific task in an almost optimal way. And I have to tell you, I go with trial and error. I haven't found out here a complete analytical understanding how they intercorrect, so I go with trial and error. If you have a better explanation, if you have a deep dive already in this topic, please leave us a link in the description of this video. So you see, from the 16 LoRa configuration parameters, we just touched about the intercorrelation between the attention dimension and the LoRa scaling. And you see, it is already beautiful. I don't talk about the other 14 parameters because I would be here for hours, but doing multi-LoRa, it opened my eyes how much opportunities I still have in the optimization of a single LoRa low-rank approximation. Beautiful. In my other video about RAG and PEFT and LoRa, you know this. And I've shown you, hey, if we take here our LLM, all our weight tensor, and then we inject here our adapter weights, and we move from 2-dimension here to 3-dimension, we have here our plane that symbolizes all of our weight tensors of our pre-trained LLM, for example, that has the task of learning English. And then we have here the PEFT LoRa approximation, where we inject additional tensors into our structure and in additional layers, as I just showed you, for some specific downstream specific task learning. Great. But now with this opportunity that we have now those PEFT adapter LoRa configuration that we can design, of course, we do not just stick with one adapter, but we can build our architecture of our transformer architecture with multiple PEFT LoRa adapters. For, and here the example, the downstream task is a question and answer functionality of our LLM, or you go for an additional coding LLM functionality of your basic pre-trained LLM. So you see, whenever you have, let's say, a Mistral 7B here as the base model, the pre-trained model, you can go now with a parameter-efficient fine-tuning for a specific task. You set your transformer layer architecture in a particular way to achieve the maximum benefits of this optimization. And for another downstream task like the coding capabilities, the code completion of a Mistral model, you have to fine-tune this, but not the fully fine-tuned, but a parameter-efficient fine-tuning with an adapter that you inject in addition. And then comes this question that is really amazing. How you combine those multiple PEFT LoRa adapter layer multiple tensor structures. What you do with those thousands of tensors? Do you multiply? Do you add it? Do you concatenate it? Do you take the complexity of it and you apply a single value decomposition on its complexity, or what you do? And if you are excited about this idea, how you can combine now multiple adapters, well, this is the reason why I did this video and this deep dive. Now, you know, those wizards at Hugging Face, they created now a coding library they call PEFT. And in this library, if you go there in the reference to the tuners, you have here for the LoRa, you have add weighted adapter. So a script they already coded for you. You can just use this command and it does all the work for you. And it is such a beautiful thing. Use this. It is gorgeous. So what it does, this method adds a new adapter by merging the given adapters to the given weights. So the parameter of this command are rather easy. You have an adapter list, so the list of your adapter names. So for example, code or Q&A or adapter 1 or adapter 2 or whatever you constructed. So the list of the adapter you want to be merged. And then you have the list of the weights for each adapter, and then you have the name of the new adapter. Genius. And then comes now the interesting type. I told you how you combine this. Now they coded 3 possibilities. They encoded here, as I told you, the SVD, the linear, or the concatenation. However, if you use concatenation, careful. We are trying to reduce here some GPU node manifold. So if you use now cat combination type, be aware that the rank of the resulting adapter will be equal to the sum of all adapter ranks. So it is a really high dimensional adapter rank that I think can come close to full fine-tuning. So careful not to become too big, and out of memory error will happen really fast. You have some optimization. I don't want to talk about this right now. But if you want to add here the adapters, this is the command. And then, of course, if you want to merge and unload this. So what is it? This command, this method merges now, as I showed you, the specific LoRa layers into the base model. You can have a progress bar and you can have save merge if you want to check if do you have some NAND in the adapter weights, if everything is full with adapter weights. Beautiful. Simple example. Couldn't be easier. It's all done for you. You just have to apply here this code base. You have your transformer library, you have your PEFT library. You take here a Falcon 40B model as your base model. And then you take here a PEFT model. And here we already have on Hugging Face this done. Falcon 40B, yes, we can do quantized LoRa. We have here an integer 4 quantization. And we use PEFT LoRa. And we have here a SFT trainer from Hugging Face. Go there, you just say, hey, PEFT model from pre-trained to the base model, the PEFT model, and you say model.merge and unload. And then you have here merged your LoRa layers into the base model and you are ready to go. Isn't this beautiful? But of course, there's also a second way to go. Instead of just adding the layers to your model, the LoRa layers to your model, as I showed you, if you know exactly this is the architecture I want to go with, you can merge also the active adapter weights into the base weights. So what you do not build a more complex architecture of your transformer layers, but you bring it down all together. You merge each and every adapter weight to the base weight. And if you look here at the original code here at PEFT source, PEFT tuner LoRa, the layer Python file, I have here a screenshot for you. In line 219, you have here for the linear layer, you also have it for the embedding layer, but let's stay with the dense linear layer. You have here the merge command, but now we do not merge the layers, but we go down to the explicit adapter weights and we merge them into the base weights. And most important is here, the weight data 0 plus equal the get delta weight of the adaptive adapter, and you just append this. So if you know that you never want to uninstall your adapter, you want to separate your LoRa from the base model. If you think this is my optimal model, then for speed improvements, for cost improvements, merge the weights into the base weights. Otherwise, and this is the other way I would recommend, go with the layer integration, because then you have another beautiful option that opens up to you. I will show you this in a minute. So just a summary. So either you merge your LoRa adapter weights into the base weights. I just showed you the code. It is much smaller. However, it alters now the base weights of our LLM. So there's no way back to go back to the original LLM. You reduce the memory overhead, but however, as told you, this is not reversible if you decide, hey, now I want to again go back and extract this LoRa adapter and exchange it to a different LoRa adapter. Then this is done. Or, and this is what I use currently, I change the architecture of the layer itself, the complete model architecture. I integrate the low-rank LoRa layers to the original layers. I increase now, of course, the computational overhead a little bit with this architectural change of my transformer layer structure. But I know I only go with low-rank layers, and I hardly go over R4 or R6. So R10 is already unusual for my specific task. LoRa layer can not only include adapter weights, but also some associated component normalization layers. You can, as I showed you, define here the target modules for LoRa. You have an extreme portfolio of optimization where you want this matrix factorization applied, and you can specify it on each layer and on each tensor. Beautiful. If you go with the second method that I use, there's another opportunity you have. If this is, for example, your LLM architecture, now you can enable and deactivate now different LoRa adapters. If you have your model now and you say, hey, I just want to fine-tune this only on code optimization, and I'm not gonna use here chat functionality or question and answer functionality, you just deactivate here this particular specific PEFT LoRa adapter. And you have your code optimization. So this is very nice. If you go multi-PEFT LoRa, this is the way to go. But of course, you can change this. You can change another configuration. You can say, hey, no coding, just optimize my chat in the parameter efficient fine-tuning task. Then you go with this adapter. So switching on and off multiple adapters based on your beloved pre-trained LLM. You can do this for your personal data set, for your personal fine-tuning behind your corporate firewall. You do not have to go outside and be visible to any other global corporation or maybe competitor. So this gives you here this multitude of opportunities to fine-tune for multiple downstream tasks. Okay, now just to show you this, to give you a feeling what happens if we do this and we build our LoRa model. I just go there and I take here from Hugging Face here from the PEFT testing here a tiny OPT or LoRa model. And now we look again at the architecture of this model. And now you see what happens. Look at this. We have again our pre-trained model, and then we have here a LoRa injected tensor weight additional layer. But this is not the correct idea, because we can choose each tensor and each layer that we want to apply this on. So let's have a look here. And this now is much more interesting, because you see, and let's focus here on this blue block, we have here our OPT attention mechanism. The attention is here all that are indicated with red. And then we have, of course, the activation and the layer normalization. And then we have here the multi-layer perceptron for our feed forward. Those three are the last from the MLP. But let's look just at the self-attention, where we can apply LoRa on. You see here our three weight tensors, our key, our value, and the query for calculating the self-attention itself. Here it is chosen, like in the original literature, to go here with the value and the query tensor and not apply LoRa on the key tensor. So if we see here in the layer architecture, you see here K project linear, and then here on the value, we have here a linear, but then we have here our LoRa A matrix, our LoRa B matrix, and our LoRa embedding A and our LoRa embedding B. And then you have the linear layer and the same here on the query structure. Our LoRa A matrix and our LoRa B matrix. So if you look at this a little bit more magnified, you see now that you can choose where to apply this beautiful matrix factorization methodology to project to a reduced subspace which has all the most important information. Let's say 90% of the complete space you have now distilled down to a smaller subspace, and you operate in this subspace. And this is, for example, a way you can build your LoRa architecture. But if you see that you want to integrate here, for example, for the multi-layer perceptron, also a LoRa architecture, go do it, experience it for your specific task. The speed improvement can be amazing. And you can do this, of course, also from the quantized LoRa methodology. I'll show you in my next video the code. So now we understand LoRa is a powerful idea, and you have to choose in your particular pre-trained LLM on what architecture elements you want to apply LoRa for the most important effect, for the best performance improvement. And this is a non-trivial task, believe me. Great. So for Ben, again, I wrote down what all the different layers are: self-attention, attention, self-attention, layer normalization, and everything else. Ben, this is for you. So let's code. Finally, now that we understand what we are doing, what factors, what parameters we have to alter, to modify, to optimize, and how the parameters are interrelated between each other in the set of the parameters, let's look at some simple PEFT commands. Okay. First job is we load a PEFT adapter model from the Hugging Face transformer. This is the easiest thing we have. So transformer, PEFT model ID, you choose a LoRa model on Hugging Face. Choose some expert, please. We know here our Hugging Face wizard, and he went here with the opt model, just the 350 million free trainable parameter, and did here the LoRa optimization. So we say model is auto model for causal language modeling from pre-trained, and then we load here the LoRa model. Beautiful. You can have a different command structure. You can say, hey, my original pre-trained LLM is the opt350. Then I have a PEFT model ID as before here, the LoRa. And then you can say, I just go in the classical way with the auto model for causal language model from the pre-trained, and we go here with the Facebook opt350. And then I load the adapter command. And then you have here your model, your Facebook model, the pre-trained model. And on this model, you load the adapter model. And this is your PEFT model ID. This is the model, the LoRa model that's available in Hugging Face. So however you build your way, these are your options. Great. Now that we have loaded, we have to edit. You can have add adapter commands. You can use PEFT library, PEFT model, add adapter to add a new adapter to a model with an existing adapter. Multi-LoRA is our topic here. As long, this new adapter has to be the same type as the current one, so you cannot mix decoherent adapters that have not the same parameters. All has to be from the same type, the same form, and the same beauty. Okay, if you have an existing LoRa adapter attached to a model, pre-trained, yes, Facebook, the same opt350, we load our model, and then now we have here our, as I showed you, the LoRa configuration. Remember the 16 parameters? And then we just pick out 2 that we want to alter the default values. We don't want to have it initialized, beautiful, and our target modules are our query projection and our key projection. And then this is now the way how we want, on what elements LoRa should be applied to on this too. And then we say model add adapter. Of course, the adapter has to have the LoRa configuration where we tell it, hey, this is the places where we want LoRa to be applied to in our layer structure. And you can give it a name. Let's call it adapter 1. And then if you want to add now another adapter, and it can be, for example, the same configure, the same LoRa configuration, you add now adapter 2 to this. This is the way that you build here adapter on adapter. Another way. The beauty with this is now you can use the set adapter command to choose which adapter to use, to activate if you want. And this, the command is a recent command, model set adapter 1, or if you want to activate adapter 2, model set adapter 2. So you can choose, as I told you, in the layers, if I want the first pink layer or the second pink layer, adapter 1 or adapter 2 activated for the parameter efficient fine-tuning on my fine-tuning dataset. So you alter here your transformer layer structure and the complexities of the fine-tuning mathematical operation. Beautiful. Another command you should know is enable and disable PEFT parameters, PEFT adapters. Because once you have added the adapters to your model, as I told you, you can enable them or disable them. And the command is relatively simple. Here, model.enable adapter. And here you have the complete code. So again, you have the transformer library, the PEFT library. We go again with Facebook Opt 350. We go again with the LoRa adapter model that we have. And then we say, this is the model, Facebook, and the PEFT configuration. We have now from our pre-trained PEFT adapter model, the 350 LoRa model goes in here. Either you choose to initialize all the random weights, yes or no. Then we just say, hey, now we add the adapter in the PEFT configuration. This is here our LoRa configuration. And then we enable the adapters and we do here our output calculation. So simple commands we're going to use when we code now in the next video the complete example. Yeah, and disable, of course, if you have your model with your multi-adapters PEFT LoRa structure, you can go and say model disable all the adapters or some specific adapters or whatever. You can switch it on, enable it and disable it. Beautiful. Wow, this was quite some topic. But we do this to apply this, to build now in a new code example, our new coding LLM. And we built, for example, a coding LLM that can chat with us. So let's code together. So what we do, what is the first task? We want to build here a personal code LLM. And the task is simple, a code completion task. You know this from Windows, the Copilot or whatever. But now we do it. This means we choose our training data set for this. We can take, for example, all the code that your company generated and that is not available to the public. So whatever, or you have coder that you say, hey, I want to code like person A, B, C. So you go there, you take their GitHub repos, you ask for permission, of course, and you get here an absolute AI system where a code LLM is, for example, especially trained here on those wizards that you say, I would like to have a code like they can generate it. You know me, a little challenge we do here just to get a feeling, a full fine-tuning. Yeah, code a full fine-tuning. And we use here the PyTorch fully shorted data parallel technique, or FSDP if you are an expert. But of course, we just do this as a warm-up, because the real interesting thing is if we apply now the multi-PEFT LoRa, everything we learned today, now to the complete coding example. So we just want to have a full fine-tuning, but we go here with a parameter-efficient fine-tuning of our own personal code LLM. But now we have a code LLM that does a code completion task, but we want to add another functionality, a chat functionality, a question and answer functionality, whatever you need on your private data, we're going to build this. So Multi-PEFT LoRA opens up the avenue for coding this. We have a pre-trained LLM. Take whatever you need. You can go with a Code Llama. You can go with Ever, StarCoder, or whatever code LLM you have access to. And then we can start not fully fine-tune, because this is very expensive, but parameter efficient fine-tune this with one specific efficient fine-tuning methodology, and we will go with a low-rank adaptation of our matrix factorization task to bring down the complexity but achieve here excellent performance. And of course, you notice now PEFT is seamlessly integrated with Hugging Face Accelerate for large-scale model, leveraging here deep speed, and we will go here with the deep speed optimization. So this is, I think, the outlook. I make here an interrupt for today. This is now the coding we're going to do in the next video. But now you know exactly what I mean when I say here, we have to be really careful here in the parameter tuning of our PEFT LoRA configuration, and especially if we do a multi-PEFT LoRA configuration, because here, if you do not take care, some bad things can happen and you have here parameters that just go wild. Okay, this is the coding exercise for the next video. I hope you enjoyed this video the way I did it. I think it built up from a single PEFT LoRA optimization technique, and we are now able to do the multi-PEFT LoRA implementation. I hope it was informative, and it would be just great to see you in my next coding video.